All right, class and fellow scientists, let's look at Chapter 22, Section 4, Plate Tectonics. This is fascinating. This is absolutely fascinating that we live on an Earth where the ground beneath us is actually moving and shifting. This is phenomenal. I hope you enjoy this section. This is really cool. All right. This idea of plate tectonics was mind-blowing for scientists when they came up with this concept and actually then gathered evidence to show that this is true. So the idea here is that plate tectonics is this theory that pieces of the Earth's crust, specifically the lithosphere, and these are called plates, is actually moving. The Earth's crust is actually moving, and it's moving slowly. Okay, granted it's slowly, but it is moving slowly on top of the liquid below the plate. Remember, the mantle has the lithosphere, which is actually solid and kind of part of the crust, and then it's got the asthenosphere, which is liquid, and this is where your currents are happening underneath. Those currents then are going to affect the crust above it. So the theory of plate tectonics explains the formation and movement of the Earth's surface, these different sections of the Earth's crust, which are called plates. Okay? You should know how this theory was developed. So in early 1960s, there were some geologists who could not explain why there were mountains in some places and oceans in others. Nor could they explain how fossils of ocean creatures could be found on top of some of the highest mountains. Okay? So they had to start answering these questions. And they had to figure out, well, let's come up with a theory that would explain this, and plate tectonics helped geologists to answer some of these questions. All right, let's dive into it. So the idea here is that we still don't have a full grasp of it, but the idea is that that over time, what was a solid landmass, okay, it was called Pangea, or they call it Pangea, moved and shifted because of the currents underneath the crust. Because of the currents and these different plates, they started to then drift apart. Okay? So the hypothesis, or the idea, is basically that the continents were once joined in a single supercontinent, but then, due to the undercurrents, they broke apart and they moved further apart, and are probably still moving apart. Okay? Some of the evidence that was used to develop this theory is the shapes of the different continents. They discovered the shapes of the continents and noticed how well the shapes actually fit together. And then they also looked at fossils of land-based plants and animals on continents were on continents that were separated by large oceans. Well, how did the fossils get on this continent and this continent if there was a huge ocean between them? So the theory was, well, they were once very close together, or even touching. Okay, so these ideas then led to this theory. Again, it's a theory because there's no way we can know for sure. Nobody was alive. We have no empirical evidence that Pangea actually existed. We're just using the evidence that we have today. Okay, so you need to know this term Pangea. You need to understand that due to continental drift and because of the movement and current underneath the Earth's crust, that there was continental drift, and those land masses broke apart. Those plates started to shift and pull those land masses apart. Okay? All right. There are some problems with the theory. So some of the problems is couldn't quite understand or explain how the continents could plow through solid rock of the sea floor. And Wagner, who was one of the originators of this hypothesis, he was unable to give a convincing explanation of what force could move entire continents. All right? So initially, the whole idea was rejected. But then some further evidence, new evidence came to light, and that new evidence, all right, here's some of the evidence that helped support the idea of continental drift. Basically, it was discovered on the sea floor that there were areas on the sea floor where separation was occurring. Okay? So, the idea here of a mid-ocean ridge. Mid-ocean ridge would be an area, a line at the bottom of the ocean where it's pulling apart. So underwater mountains, they call these mid-ocean ridges. How are these being formed? Basically, you've got two areas where the oceanic crust is going in opposite directions, and as a result, you've got molten rock that is coming up into that space and forming, and then cooling down when it's the water, obviously, and then forming a ridge there. Okay? So that was evidence that the plates were actually moving. Other one, formation of oceanic crust. So the idea that the seafloor is spreading, as mentioned before. So data was collected, and they realized that these two crusts are actually moving apart. All right, so when that was discovered, that was further evidence of the idea of continental drift, and that maybe at one time all these continents were one big landmass. So this is a great diagram here where you need to maybe be able to interpret this. If I gave you a diagram like this, you should be able to identify a place where plates are moving across, away from each other, and this would be a mid-ocean ridge. This would be where magma is coming up and filling that space and maybe creating a little tiny mountain, not tiny maybe, but a mountain under the ocean. You need to know that if you have a place where two plates are coming together, and this would be an area where one is going below the other. So here you have continental crust and oceanic crust. Because oceanic crust is denser, this is where you have convergence. So because of the currents here, the currents would be pushing these towards each other. All right. Here you would have maybe an area where magma is coming up through the continental crust and forming mountain range. So if a diagram was given to you like this, you should be able to identify some different regions or different areas and what is happening in those different regions. Okay, so you might want to study this diagram and learn a little bit about the different terms there. All right, I mentioned already this is the idea when you have two plates coming together and they can either be convergent or divergent. So a sea floor spreading occurs. The oceanic plates sink into the mantle in the process called subduction. That subduction basically is going to be where it occurs because the oceanic plate moves away from the mid-ocean ridge, and then it cools and it becomes more dense. So it's going to basically, sub means under, right? It's going to go under and turn back into molten rock. Seafloor spreading and subduction together act like a giant conveyor belt. So here, let's look at this. This is something that you need to understand. This is a key point. Seafloor spreading creates new oceanic crust in mid-ocean ridges, and then subduction is going to actually destroy old oceanic crust at subduction zones. So let's go back up to this diagram. This is where new oceanic crust is being formed. We have a divergent meeting here of plates. These are pulling apart from each other, and the magma is coming up and filling in and creating new oceanic crust. Here you have subduction. You've got this plate and this plate that are coming toward each other, and subduction is happening because this one is getting forced down and then is going to turn into the asthenosphere. It's going to get, because of the increase in heat and pressure, it's going to turn into molten rock. Okay? So you need to know that sea floor spreading, that's where new oceanic crust is made, and then subduction is going to destroy the oceanic crust and it's going to push it down. All right? We already mentioned that the evidence for sea floor spreading was at the mid-ocean ridges. And then this all leads to and helps support the idea of plate tectonics. All right? The seafloor spreading was what was missing in Wagner's hypothesis, so it added some evidence and then bolstered his theory on plate tectonics. So, according to this theory, the Earth's plates are constantly moving, each with a different rate and direction. Why are they moving? Because of the currents below in the asthenosphere. So that plate moves and are a visible part of the process of the mantle convection. What that means is basically underneath in the mantle you've got different currents. Those currents, we can't see them obviously, but the evidence we do see is the motion of the crust. So the formation of mountains or subduction or mid-ocean ridges, all of this is evidence that below the crust there is movement that is happening and forcing the crust to move itself. Okay? The process that drives plate motion, here's a key point, on the Earth's surface is similar to convection in a pot of boiling soup. So if you were to place something that floats on top of your soup, or maybe 4 different pieces that float on top of your soup, you're going to see those things that are floating on top of the soup to be moving because of the currents underneath it. Okay? The heat that drives convection in the mantle comes from 2 sources. Well, it comes from the core. So the Earth is very hot when it's first formed. Some of the heat moving upward in convection currents is due to the gradual cooling of its interior. And the second is because of radioactive isotopes. You don't really need to know that. But basically you just need to know that the heat that is happening inside the core is going to cause movement of that heat, convection currents, and that affects the crust above it. That is your key point in this section. Okay? Now, where these different plates meet, we have plate boundaries. And there are about a dozen different plates, major plates. And they may be containing continental crust or oceanic crust or a combination. And they meet, and those meeting places are called boundaries. And there are 3 types of plate boundaries. We talked about this. Divergent. Divergent means that their plates are moving away from each other. Convergent. Convergent means they're moving towards each other. And then transform boundaries, and let's talk a little bit about that one and be more specific here. Okay? So plates move in different ways. That's why these are different types of boundaries. It's basically how the plates are going to move. They move apart, they collide, or here's your transform, they're going to slide past each other. So they're going to move like this. Okay? Here's a map of different boundaries, and you'll see in red you've got convergent boundaries, green you've got divergent boundaries, and in blue you've got transform boundaries. So here the plates are moving past each other like this, In red, they're moving towards each other. In green, they're moving away from each other. This is just further explained right here. So you might want to spend a little time in summarizing each of the types of boundaries. And these images are showing you exactly what's happening here. You need to know that at divergent boundaries, since the plates are moving away from each other, you've got new land or new crust that is being formed. And here, when you have convergent boundaries, you've got crust that is actually being destroyed. It's being pushed down into the mantle and basically turned into molten rock. Okay? Here, transform boundaries, you're probably going to have an area where there's going to be high probability of earthquakes because of the shifting land and the rubbing and the pressure that is formed and building up in those areas. Okay? All right, along these different boundaries, you're going to see different structures. So you've got mountains that form at plate boundaries, especially at convergent plate boundaries. And you're going to have volcanoes and you're going to have earthquakes. So the idea here is that not just mountains, obviously you have mountains here at the plate boundaries because they get pushed up, but you're also going to have other geological structures and happenings at these different boundaries, as is diagrammed here as well. So you might have earthquakes, you might have mountains and volcanoes, you might have magma coming up, okay? So these are very active areas on our Earth's surface because of the meeting of these different plates at these boundary regions. All right, that is really the 22.4 and all you need to know there.